Hello and welcome to this Falling Walls Circle Table. I'm Zulfi Karabani, a senior science editor with DW Deutsche Welle, and this is the next big machine. Does Cern need a new supercollider? Now, the Circle Tables are a chance for global science experts from academia, business, and politics to exchange ideas for a new tomorrow. The Circle Tables are part of Falling Walls 2020 and the Berlin Science Week and Remote World Science Summit family. Trust me to weave a tongue twister in my opening lines there. In a nutshell, what are we here to talk about? Well, what good are particle accelerators, and why does Europe need a new 100-kilometer ring, a future circular collider, when it's already got the Large Hadron Collider? The future circular collider would be about 4 times as big as the LHC and roughly 10 times as powerful. Now, who needs that? Well, we're going to find out and what it will take. On our panel, we have speakers who are truly at the top of their field. Ursula Basler, for a start, president of the Cern Council. Cern, as you know, is the European Organization for Nuclear Research and the home of the LHC. Ursula is also deputy director of France's National Institute for Nuclear and Particle Physics. Jeremy Farrar, director of the Wellcome Trust, a global health expert, a specialist in infectious diseases and emerging infections, very much the glue, I believe, here between the physics and society. Beate Heinemann, a leading scientist at DESY, the German electron synchrotron, and a member of the Atlas experiment at Cern, trying there to discover the secrets of the universe. Do let us know if you find them, Beate there. Nigel Lockyer, director at Fermilab in the States, which I believe wants to be the world leader in accelerator-based neutrino research, which involves building huge underground facilities, not unlike the LHC. So welcome to all of you. I should also finally say thanks to Rolf-Dieter Heyer, former DG of Cern. The Circle Table is supported by the Wilhelm and Else Heraus Foundation, where Rolf-Dieter is a member of the board of directors. So thank you very much to Rolf for organizing this for us. And also, hello and welcome to our audience. We hope you are plentiful and here to stay for the entirety of this hour. Hello, everybody. Now, I want to go into our introduction here because we've got a chat running, and don't be shy. I want you, the audience, to ask questions. There will be a chat, a Q&A, a chance to have a chat with everybody at the end of the session, but I will also try to take questions as they crop up throughout the session. So I hope that that chat is now active. We'll just check in with that in a second. Now, I imagine if you're here, then you've read the blurb. So for those who haven't, let me give you a quick précis. With Cern's Large Hadron Collider in full swing and scheduled to run into the late 2030s, this might seem a strange time to be proposing a new particle accelerator in Europe, but that is actually what the latest updated European strategy for particle physics has recommended. They would, wouldn't they? You might think. Well, we're going to split this up now into 3 different sections. An overview of the science, then a bit more of the science and the technology, where we're at and where we have to get to in order for this to work, how things could be different. Could we look at alternatives for particle physics? And then, of course, the politics and society. Now, I'm going to just scroll through my notes here because I need to get to this section here, our first sort of little to and fro here. It strikes me that the title of this session harbors one grave assumption, and that is that we need any super colliders at all. Yes, I am being facetious, not least because I've been warned not to use the term super collider too often, but perhaps you could indulge me here. Tell us why you think we need particle accelerators. CERN already operates, as I say, this 27-kilometer ring under the streets of Geneva. And now you want a 100-kilometer machine. How do they help your work? How does that help the rest of us, society? And perhaps we could do this alphabetically. Ursula, is CERN being too greedy here?
Well, I just wanted to give a little bit of the context first. I mean, CERN is operating currently the LHC, the largest hadron collider that exists. However, this collider will still take data for another 20 years. So we don't talk about building a collider now. We talk about what should come afterwards. If we want to make further progress into particle physics, then we need at some point to go to higher energy. Therefore, we need a bigger machine. Now, the European strategy essentially started to think and started to plan how can we get to a future machine. But again, as I stated, this is not for now. This is the start of the planning for what will happen in 20 years and then go on for about 50 years. And it includes not just one collider, but actually two colliders, an electron machine in order to make very precise physics, and then another hadron machine later on, maybe in the 2050s, in order to go explore what is happening at the very high energies.
So we can get into that a bit deeper in a minute, but that does seem that basically CERN is being quite greedy, isn't it? And I wonder whether we have to look at this machine here in Europe. I mean, you know, what about Southeast Asia? What about Africa, the Middle East? And just think about the Sesame facility in Jordan. Jeremy, as someone who has, for instance, worked extensively in Vietnam, what are we missing with these huge science projects that seem so invariably to be Europe or US centric, at least in the public's consciousness, and mine indeed?
Yeah, it's a good question. It's a pleasure to be here, by the way, especially as my knowledge of the science of the discussion here will be stretched beyond its limits. Firstly, I think, and those of us not in this field, I think it's easier for us to say this. The role that CERN plays as standing for international cooperation and collaboration in science, in partnership, of course, with colleagues in America as well, at the very large facilities there as well. But CERN really does set the standard of this. And yes, the facility is under the streets of Geneva, but this is one of those really truly global partnerships and collaborations. People from all over the world, whether from Vietnam or South America and everything in between, can use these facilities, because you can't have this sort of facility in multiple parts of the world. There can't be that many CERNs. But as an open, transparent, welcoming centre, I think it sets the standard in science. Certainly, we in the health arena have got a huge amount to learn by the way CERN and particle physics in general goes about this as an international collaboration.
Well, that's very interesting you mentioned that, Jeremy, because of course, the times that we're living through right now. Beata, now, you're based in Germany, but I mean, you've also been in the States at Fermilab. Nigel, we will come to you in a moment. Tell us, what is that like? I mean, that collaboration, if these machines can't be everywhere in the world, do you have to go to Fermilab to do particular science, for instance?
Yes. I mean, I think this is actually exciting in particle physics that we've now, I mean, in the 60s, it was that each country or each continent had their own facilities and they were competing with each other. But now the projects have become larger and larger so that we actually collaborate with each other. I mean, of course, there's still competition, but by and large, we try to maximize the world's potential for science. So for instance, neutrino physics, which is a super interesting particle, the neutrino, that if I wanted to excel in that, then I would go to the US or to Japan, while for the energy frontier, which is what we're talking about, this collider, Europe is the best place at this stage. So I think, so this is really just an, well, at this stage, yes, that's right.
Because there are other competitors out there,
yeah,
aren't there? I mean, you know.
Right. I mean, I think, yes, definitely. I mean, so there's similar proposals in China, and there is also an alternative proposal in Japan. And these are also very interesting. I mean, it's not clear. I mean, as a European, also we'll get to that later, I think the societal benefits, it seems sort of selfishly that having it in Europe would be best. But for science, you could, of course, argue that it could also be elsewhere.
Okay, right. So elsewhere, the United States is one of the obvious choices, I find. Nigel, I've got to say, I'm sorry, supercolliders. Tell us about the superconducting supercollider. This is a project, what was it, about 30 years ago? It got killed after spending about $2 billion. let's not dwell on the past too much, but what has changed since then in terms of the science and technology, and perhaps also the public and political mood or will for these huge machines?
Well, I would say what's changed from people's curiosity about our field is not very much. I would say that people are still very interested in understanding what's sometimes referred to as inner space, or what are the smallest entities in the universe. And that was true back then, and it's I would say even more true now. I think Cern has put particle physics on the world map in a way that we've never experienced before. Everybody seems to know what the Higgs boson is, and so that drives people's curiosity to understand what's this all about? What's this field all about? And it's not so different from wanting to go into outer space. It's you want to look at things you don't know about.
That's a really nice point, and I think we will probably come to that in a moment. I imagine that there's a growing interest because people are looking up higher above their heads into space with all the talk about Mars and moon exploration again and that sort of a thing. We do actually have a question here already, and I'm very happy to say, and that allows me to get back to Ursula now. Let's talk a little bit more about the future circular collider. We've got a question here that basically asks Ursula, is there a guaranteed goal for the next machine? Can you sort of couch that in a little bit of a bit more background into what you'll be doing? You spoke about higher energies and that. What is a guaranteed goal? Why do you want this now, or in 20 years or 30 years?
Well, the first thing that we want to do is to understand the Higgs boson better. I know that there is a kind of idea that, well, you found the big Higgs boson, standard model is complete, been there, done it, so let's forget about particle physics. But science is not working this way. When you discover a new thing, then you really need to study it in great detail in order to understand all its implication. And for the Higgs boson, especially also the implications on cosmology and on our understanding of the early universe. I think this is, for me, the most interesting part of it. So,
Higgs boson, just remind us of the importance of Higgs boson, this sort of glue of the universe. It has been some years since it was detected at the LHC, hasn't it?
It has been discovered in 2012. It has been the missing piece of the standard model, and in some sense, if you say it broadly, it gives the mass to all the particles that are around us. So without the Higgs boson, the universe would not exist in the way it exists. However, it could also have played a quite interesting role in the primordial universe, in the moment, in the first couple of instants after the Big Bang. And I think exploring further the properties of the Higgs boson will allow us to understand better what happened at that moment. And this is the first goal of physics that we will do. Then the second goal is to move to higher energies and to explore.
Okay. I mean, you mentioned there also the standard model and how sort of the universe evolved and but it's basically how we understand the universe to have evolved, isn't it? I mean, if we couldn't prove the standard model, then basically we'd have to start a whole patch of scientific endeavor again, wouldn't we?
Indeed, we would, yeah.
Okay,
well,
yes?
but
yes, go ahead.
But I mean, wouldn't that be exciting?
Right, that would be exciting. But I mean, the thing is that when you think about the universe, I mean, okay, at least the mainstream theory, we think that it started with a Big Bang, and it was at very high energy, and we think that the energies, I mean, so what we're doing with these colliders is making very high energies that have not really existed since that time of the Big Bang in a way that anybody can look at that. So with the LHC and then even with the FCC, we're basically producing energies that were there during a phase of the universe which was critical, which was a billionth of a second after the Big Bang, where it fundamentally changed. It was so our theory says it was symmetric before, but then the symmetry was broken, which actually generated all the flavor in the universe, and most literally the flavor in the universe, making it so diverse. And so it's just really a very fundamentally interesting phase of the universe, at least according to our mainstream understanding of the theory. So
can I also just try to bring this back down to earth just a little bit, because and I don't mean that in a negative way. I just mean, you know, finding out how the universe began, and that has a reflection not only on the greater universe, but also on our very close universe to Earth, doesn't it? Which means that we're able to tie in different aspects of science. So this particle physics also has a ramifications for Jeremy in his work in health. How do you feel about that? I mean, you know, is there enough of a crossover, Jeremy and Nigel as well, to both of you, between these sorts of, in a sense, I'll be quite rude again, sort of abstract forms of science, but then also very immediate forms of science where we can see an impact, perhaps even a larger impact, what we call maybe small science, but with a larger impact, medicine and that sort of a thing. How do you both feel about that?
Yeah, I don't see it as a zero-sum game. I mean, it's incredibly inspiring to join this group, but also hear the broader discussion. My only question back actually would be the opposite of yours: is, are you being ambitious enough, or are you fitting it into a predefined budget? Because, you know, 20 years from now, are you going to think that that thing under Geneva streets just wasn't big enough? And most people, I don't think, are ambitious enough in these sorts of big projects, to be honest. But I think I'm really interested in the indirect consequences of stuff that we may not know. We may not even know we should be asking those questions. The inspiration it gives to the next generations of scientists, the sort of conversation we've just listened to here, people that will go into mathematics or physics or chemistry, and then come into biology or into healthcare, and then the whole of society will benefit when they go into other aspects of working life as well. So I don't think we can just say, what are you going to give directly by doing these things? It's the dramatic impact it has on the whole of society, and frankly, something akin to a modern enlightenment.
I mean, that's a very, I'd say a very generous, if I can speak for all of you, that's a very generous sort of take on it, because we had a chat the other day, and there was this idea that perhaps sometimes physics overstates its importance. I mean, Nigel, how do you feel about that? It would seem as though physics cannot overstate its importance in science and all sciences, listening to what Jeremy just said.
It better not in this case, because it's a big investment by the globe. So, but I would say that, you know, you asked a question earlier, which was, you know, are we ready to build this machine? And the answer is no, we're not ready to build it. The technology's not there. So what does the scientific community do to prepare for something like this monumental undertaking, if you like, in terms of constructing, you know, what will clearly be the most ambitious scientific project on the planet at the time? And the answer is you have to have an army of scientists doing research and development. And they'll have to do this for a couple of decades. And that, by definition, will create discoveries, create innovation, and it will eventually impact what type of science that Jeremy does. I think it's not something you predict. It's just something that happens. I sometimes facetiously say that, why does particle physics have to impact anything anymore? The World Wide Web was discovered by Cern. It's impacted the world economy with trillions and trillions of dollars of commercial activity. We're finished. We've done our job. We're looking to the other fields to actually do some work for a change. So I feel pretty good about where we are. But we didn't predict that. The important thing is we didn't predict it. And so a lot of people doing research, a lot of smart people, and I'll say our field tends to attract extremely smart people, that good things happen.
Well, dear audience, that's it. You know, Nigel has said the final word, that we don't have to prove ourselves anymore, or certainly these scientists don't have to. No, only joking. Please stick around. don't forget, you can ask questions. So do, I hope there are more questions coming in, because the debate is only going to get hotter. Because Nigel, you picked up on something there, this idea of the technology, whether it's there or not. And I mean, how do we get there, and where is there? What sort of science do you really want to do now, and what would it take? I mean, let's be realistic. Are we still thinking in boxes that that will limit your ability to think of new science projects, and also think of the technology that you'll need for those science projects? Nigel?
Was this for Nigel?
It was originally, but anybody who wants to pitch it.
You're forcing me to answer my own question now.
Well, I can.
Or Beata, go ahead.
Well, I mean, there's so many things, right? So for this machine, or these two machines, as Ursula Bassler said, so for one thing we need to do is we need to make advances in superconducting magnets technology. Very significant advances. Superconducting technology is, for instance, used for MRIs, just as an application. We also need to make advances in computing, because the data that we're going to get are huge. We need to make advantage in image recognition, because the rates of particles and the densities are going to be very, very large. So the detectors that we need to use to make sense of them are challenging, and the technology does not exist yet. So it's really a multitude of technologies where we need to advance, and it's not. I mean, it's R&D, right? So it's not directly predictable. We know where we need to be, but how to exactly get there is no screen book or whatever. I mean, so it really needs a lot of scientists to think hard and to try to innovate, and then somehow hopefully it will manifest itself.
Coming from outside the field, and coming from a sort of biomedical background, where the biomedical world, I think, on the whole, has been dragged into trying to align what you do today with an impact tomorrow, and become very short thinking. My advice into this community would be continue to dream. Don't try and say that within a year, 18 months, you're going to do this, that, or the other. Of course, you have to do a bit of that, but I think the brilliant contribution this makes is pushing back those frontiers at the edges, unknown quite where it's going to take you. And from whether it's the World Wide Web or our ability to image proteins or image people with MRI machines and whatever, will come from it. And you need to be able to communicate that to the public, but don't stop dreaming, and don't get dragged, as the biomedical world has largely, into stopping to dream and to have to drive impact in the short term. I think it's led to short-term science.
It's sort of raise the idea of the usefulness of useless information. I mean, not really knowing where you're going.
No,
is that Ursula? Yeah.
No, it's. I mean, I very much appreciated what Jeremy said also about the applications. Particle physics. People come very often and say, "Okay, what is the use?" Well, yeah, you talk about the universe, but what is the use now? And and then the particle physicists start to say, well, we did that and that and that and that and that and that. And then you get a whole list, and you can estimate how much the impact is, the return factors of what you invested on the economy right now, etc., etc. But I think one should really not overrate this kind of Excel spreadsheet thinking on science. I mean, the aim is something else. The aim goes further. And it has something to do also with our human history. I mean, if we got into the Enlightenment, if we got into scientific methods, we really have to push forward also our thinking now about the universe. We cannot just stop now and say, well, it's everything that we wanted to know and we stop now. I think it would be to give in to very short-term thinking, and it would really be a loss to everybody. Yeah.
Yeah, one question I'd like to ask here is imaging was brought up in the medical sense, and there's these large so-called light sources that image viruses, for example. I know in the early days here in the US, a lot of the imaging centers, say at Oregon and Stanford and so on, were imaging the the coronavirus. And I'm curious to know from Jeremy whether he thinks that this was is an important technique sort of in your toolbox, because that imaging technology came from our field. It's accelerators that allow you to do that.
Yeah, I can answer that very quickly. I mean, it's been transformational. I mean, just go back even, I don't know, 10 years and you know, the images one was able to create, whether you call them viruses or proteins or whatever else, has revolutionized the field of being able to both image and therefore try to start understanding, yeah, how the coronavirus works, how it binds to its receptor, what you could do to prevent that happening, what you can do to look at other viruses or other proteins that you may be interested in the future. So that's a field that has just gone in amazing direction, I would say, in the last 5 or 10 years, such that you can image down to a level now which was unthinkable even 2 or 3 years ago. I was talking to Richard Henderson, who won the Nobel Prize just a short while ago for his work on this. And you know, the work you're doing on particle physics is directly linking in with the work he's doing to try and understand how basic proteins work in the human body.
And Vianney, you could say something about the Euro XFEL at DAISY, because that is sort of a state-of-the-art machine, right?
Right. Yeah, that's based on a technology that was actually initially developed for a large lepton collider, similar to so something to be used for particle physics, but is now operating since several years very successfully and for photon science, so for imaging, indeed.
So I think we're all sort of, or you're all agreed at least, that new machines are important, and this very big new machine could bring a lot of benefit to a lot of different areas of science. I'm just wondering whether, because there is this sort of idea out there in society these days, in technology, certain circles anyway, that human minds may actually have reached their limit. And so I'm wondering whether there's a way to incorporate other forms of technology, say artificial intelligence and machine learning systems, to perhaps do some of the thinking, also do it faster. I'm also thinking doing it smaller, just to throw that sort of spanner into the works. I mean, you know, we're all sort of working from home, and I think some of the other sessions are talking about working from home here. So why is it that we need these huge machines in areas that are partly residential? And so why do they have to be so big? Can't we shrink this technology? I mean, there are certain attempts to do that, such as the Awake collaboration is trying to shrink these machines. What do you think about that, using sort of simulations, digital simulations and that?
Beate may respond easiest, but I mean, we use them every day. We simulate every day. We simulate what the outcome of collisions are, what the evolution of the universe are. But from time to time, you need to compare with experimental data. Else, you could just simulate whatever you imagine. Yeah. And then artificial intelligence is also a very important ingredient. I think without artificial intelligence, the search for the Higgs boson may have taken quite longer than with using it. So it is certainly part of the daily life of particle physicists these days.
Yeah, I was going to mention that there's a new field that seems to be bursting onto the scene in the United States, which is we call quantum information science. I know it's very prevalent in Europe as well. It's prevalent in China. The world is looking at this, and that ultimately results in somebody building a quantum computer. We hear about the terms quantum supremacy and things like that, where a quantum computer becomes more powerful than the most powerful computer in the world. And what that's going to allow us to do is change the paradigm that we have now for simulating these collisions. And when scientists are driven by a goal that they have, that's what they focus on. That's what they work on 24 hours a day, 7 days a week. It's their passion. And then you get thousands of people working on that. It just moves everything forward in a dramatic fashion, especially in an open science forum. And so I can see that, you know, I bet you anything 10 years from now that we're going to be asking, what can we do with these new quantum computers in a way that the average guy in the street now is not quite sure well, nobody's quite sure what a quantum computer is, but it's definitely something that's going to impact our field, and it's something we will impact from our field.
You mentioned open
Yeah.
science there. If I could just jump in there, I mean, is there enough trust in open forms of science? I mean, there seems to still be some kind of a feeling that things need to go through elaborate processes before any science can be trusted. What is there the trust?
Well, but there is not a conflict, right? So you can have open science and it can still be reviewed. So what, yeah, so you can still have peer review and open science in parallel. That's not a contradiction.
Okay.
Yeah, but my example that I was trying to give you there was, all right, let's imagine that there's clearly a lot of interest from the private sector in quantum computing. And that is something that they'll be investing heavily in. And so they'll be interested in protecting the internet intellectual property. But for science to advance quickly, it has to be open. There has to be a free exchange of ideas. And I think that's what our field will bring to the table, is we naturally do that. I think it must be true in medicine as well, that the more you exchange information, which I think we are doing globally now, I hope we are with COVID, that's what's going to get us a solution quickly, not people trying to hang on to what they're learning.
Yeah, it's very true. Although, to be honest, I think medicine is behind the broad physics community on this. The physics community has shown the path that you can have open science, but you can also have really good science and peer review, and those can be combined together. Frankly, I think the biggest threat to that is not the intellectual property that may be gone around it to allow industrial and commercialization. I think on the whole, that's a positive thing, but we could debate that. The biggest risk to that is the rise of nationalism, in my view, and the sense that we're either competing between, let's say it, between America and China, or Europe, America and China, or all regions of the world. And if we allow that fragmentation of science and barriers set up for nationalistic reasons, then I think a lot of the current very positive sharing of science at a global scale will be put under threat.
Jeremy, I have to ask you, why? Can I just ask a follow up? Sorry, Beate. Just one, Jeremy, you keep saying that that medicine is behind physics. Can you give us a little bit more of an idea why, so that we've got a good comparison there? I mean, at the moment we're seeing work all over the world, and studies being published left, right, and centre, both in peer review, but also in preprints. Why is it not working there, and what is exactly not working in medicine?
Well, you are seeing it now, and there's almost all of it, in my view at least, is positive. There are obviously always negative, some consequences are unintended, but they're positive. But that's only been this year. It's only been through the COVID crisis that's come out. The usual time frame and the usual holding of information internally within biomedicine still has a long way to go compared with the openness that the physics community had. The inclusive nature of publications, the open review process, that's much, much more advanced in the broad physics world than it is in the biomedical world. Maybe partially driven by intellectual property being closer to the science. I don't know if that's true, but certainly the broad biomedical community is not nearly as open until the COVID era as the physics community.
Okay,
but
Beate, you wanted to say something?
Sorry.
Yeah. Well, I just thought on this global thing, I mean, when I gave a talk about the Higgs boson to scientists from many different areas, some geologist, he told me what he thought. So I asked him why he thought was interesting, and he thought what inspired him was that, for generations, I mean, we were working on this machine, the LHC, basically for generations of physicists. Thousands of physicists were involved to go after a particle that had been first hypothesized in 1964. And then we managed to actually, with a global effort, to construct this machine and to find that particle. It's like he said, it's like a fairy tale, and he was so proud of humans to be able to actually get together and do that by everybody working together. He just thought it was so inspiring, and he was actually working on geology aspect of climate research, and he thought it would be really good if one could actually get the scientists together behind such a mission in his area. But he said it's hard. Yeah.
If I may say something about it, also what Jeremy said, I think it has something that is built in particle physics, that we need to be collaborative. These huge experiments, these huge colliders, no PI could build them by themselves. You need a big community behind, and therefore you need then to find ways to collaborate and ways also to reward everybody coherently, and so to have everybody on board, even those who are not doing the final analysis, but those who are well taking care of the operations of an important piece of detector every day. On top of it, we cannot buy our machines out of the shelf. We have to develop them all together, and they're pretty complicated to develop. So the collaborative nature of the field is triggered also by the necessity how to do this kind of science. And I think then from this necessity, we learned a lot of actually how to be collaborative. And as Jeremy said, I think science globally would benefit to be much more collaborative than to be so personal or ego-centered in order to, well, you know, the best guy is rewarded with the Nobel Prize. Atlas and CMS will not be rewarded by the Nobel Prize because they're 3,000 in order to work together and get to the result, even if it's the best result in the world. Yeah.
That's not fair though, because the gravitational waves, the whole team got that, didn't they? And there was thousands of people.
No, just it's always one
No,
person.
it was three people singled out.
3 people got it.
Yeah. Okay, let me clarify that. Klaus Dunsman, who some of you may know, he said that, you know, these are the 3 people who were singled out to take the burden of the prize, but it did actually go to all the people.
But also, just very quickly, I think it also makes the case for public funding, because this is being done at a scale that it goes beyond nations that could not be funded in any other way. And public funding to underpin this over the long term is just not available from any other form of funding. And that must be continued, because it's the only way this is going to get done.
I want to, so we have, actually that sort of leads me into a question from the audience here. There was another question that I wanted to throw in, a little bugbear of mine, but I'm just going to drop it by the wayside now. What do you tell critics who say that we have bigger problems on Earth than the Big Bang? That has a lot to do with funding, that has a lot to do with the public consciousness, how people see and view this science, whether they understand it enough to believe it, to say, yes, let's stick some money into this. What do you say? We can go, Nigel.
Well, okay, so I'll say that there's, you know, simplifying things, there's 2 types of people. So when I think about talking to my senators, I have one senator who says to me, so how does this particle work? Why do we have so many neutrinos? And are you trying to tell me they're going through me now? And then we get off in a discussion about the science, and the curiosity that he shows is, to me, extremely encouraging. When I go to my other senator, that senator says, so what is this good for? And so what I usually do is I give them an example of the free electron X-ray laser that we're building at Stanford. And it's a similar machine to the one that's at Daisy. And I say, our goal there is to understand the structure of proteins. And you know that proteins, of course, are, you know, the workhorses of the cell. And if we understand that, we'll understand, you know, maybe the origins of life. We may understand the origins of disease. And so you have to have a different answer for different people, I think is my point. Some people are driven by the applications, and some people are just really curious about our science.
Let's get a little bit deeper into politics and society now, because, I mean, you know, it strikes me that, in a sense, you're trying to sell a product that the public doesn't necessarily want, or at least it doesn't really know that it wants it if it did understand it better. What do you think, what sort of proposals would you like to make now to cut across that actually very quite big divide between science, no matter which branch it is, and politics and society? Would, for instance, you know, some kind of a declaration of scientific endeavor to embed this sort of work in in a culture and a constitution of nations help to get people's minds around it? Or is it enough just to have a huge structure out somewhere where people can be constantly reminded, such as a monument from ancient Greece or whatever, that you're doing the science there, and oh yes, I remember now why I can get on this bus or I can use my mobile phone. What do we need in order to break that barrier, to have that wall fall, so to speak? Perhaps we'll start with Ursula.
Well, that's quite a complicated question, yeah. I think there are people out there that are generally interested in the science and who wants to make them over. Now, is it the majority or not? Frankly, I don't know. I just know that if we have open days or visits or science communications, there's generally a very big response from the general public to any kind of action that is done. Certainly a kind of declaration on why science is important, an international declaration would certainly be very, very nice, not only for particle physics, but for science in general, especially when some branches of society seem to lose their connection to science and to rational arguments. Now, the other question to me is also to have the spread of science being large. I mean, we don't talk about one part of science against the other. I think it's important that we have a whole scope of science that is working and that is fructifying each other constantly. Yeah? Science is also culture. It's not only about technology and applications. It's about how mankind sees itself.
Right. Okay. So how do the rest of you feel about that, Jeremy? Coming from a different field of science.
Yeah, I agree with that. It's nice to have avoided mostly COVID during this conversation. So it's been unusual for me in the last 6 months, but we can't ignore it completely. And COVID has thrust science, all areas of science, actually, of course, mostly biomedical, yes, but lots of other areas of science, including social sciences, right into the public eye, on the front page of every newspaper. And that's not going to go away at the end of it. And it's been politicized in some countries, and it's been questioned in many countries, and quite rightly so. So it's not going to go back into its ivory tower. We've got to realize that is now where science is. And science must be part of the societies which frame it and which sustain it. And I think making sure that we all see communication as part of our roles, that we all see that we need to both inspire and excite, but also explain why science is important as part of culture, as well as driving a benefit to all of our lives. And I think that is the framing of it. And we all must appreciate that's part of our roles as scientists.
Nigel?
Yeah, I was going to say that if I use Japan as an example, that the idea of a big science project in Japan is attractive to the Japanese government, I know, because they see this as something that draws the attention of young people. It pulls people into science. It pulls their interest into science. And, based on my experience here in the US, all science either rises or falls together. And I think it's important that we get in the public eye, that we stay in the public eye. And I think it'll be good for all scientists. So one of the key things here is that scientists should not look at it as a finite size pie issue, but rather the pie can grow. And that's going to be critical when we talk about the future circular collider.
But we have been talking very much from a European perspective in this circle table here because of the European strategy for particle physics. I mean, would it help, for instance, if we can't have a global declaration of scientific endeavor to combine, strategies, 5-year strategies, at least between some certain continents, and try to involve, I think Jeremy used the word societies, with the risk that may still leave some people out of it. I mean, we still have, spoken about scientific endeavor on the African continent. So how do we get that kind of collaboration? It still seems to me that we're missing a trick here. Either Nigel or Beata, whoever.
Well, I can speak from the standpoint of Fermilab, and I'll say that I think Cern takes a similar approach, is that there are countries who can pay their way and there are countries who can't pay their way. And why would we be interested in countries that can't pay their way? Because their people or their countries can produce scientists who are brilliant. And we want the most most creative people on the planet working on our project so that it's successful. So we've taken an approach here where we've have a big focus on South America and South American scientists working in the U.S. and that's very popular at our laboratory, and it's popular in Latin America. And we're going to do more of that. And I think that's the way you spread it. You have to be deliberate about it.
So, and Beata at DESY, the people who work there, it's quite a mixed lot of people, isn't it? So is it already happening? Do you have to do it direct, or does it just happen? I mean, is there a chance for it to happen organically? Do you have to force it?
Well, actually, interestingly, so I recently checked, and in our group, for instance, only 30% of the students and postdocs are from Germany, 30% are from other European countries, and 30% are from beyond Europe, other continents. So you see, there is it's very international, yeah. I do think that this is happening. We get a lot of applications from all over the world, for instance. But I do think that also still we don't really have enough scientists in the world, as far as I can tell. I mean, we really need more scientists. So I think it's very important that we inspire, that we try to make it attractive science, that we also communicate it well, and we make it attractive, that we teach it well at an early age. Kids, when they're kindergarten age, they're very curious, right? But then at some point they just don't like math anymore. Somehow we have to bridge that to foster that enthusiasm that really small kids are when they wonder why a bee does whatever it does and so on, right? So,
Beata, have you been talking to my old maths teacher? Listen, that actually leads us quite nicely into our Q&A session here. But before we do get into that, just very briefly, so we've gone through a lot of the science. There is one very tricky question here that I think I might actually just chuck into our Q&A session. But we've spoken a lot about the science, what could be achieved with a new particle accelerator at Cern or elsewhere, indeed, a larger one. We've also spoken about how to get that into the consciousness of people and to get support for it, whether it's public, scientific, or public or political, social support. I am going to just try this now. Just bear with me as I try to read this off my phone here. The question is targeted mostly towards particle physics in general. We have for more than 2 decades seen that the observer collapses the wave function to a particle. Observing smaller or higher energy does not answer the question about this process of observation. The precision have reached quite literally a billionth of a second after the Big Bang. A change of focus on other parts of the process might be called for. So, over to you, because as the Germans say, there are a few Fremdwörter in there for me. Who wants to tackle that before I get into the easier questions?
Not me.
Stunned silence.
I'm just a poor experimentalist. Sorry, this sounds pretty much like a theoretical question. I don't feel even able to open the shoestring here.
Okay. Because I mean, sort of another one of the questions here, it's actually quite interesting, is like, what are sort of alternative routes that one can take with a particle accelerator, apart from just going to higher energies? I mean, are there alternative things?
Yeah, maybe I can have. I mean, I can also not precisely answer the question, but I think none of us only want an accelerator and nothing else. I mean, it's absolutely clear that there are other and very important ways also addressing some very important question about for the universe and how fundamental interactions work. There is the neutrino experiments at Fermilab. There's also smaller scale experiments that are, I mean, like our version of tabletop, if you like, that do very interesting and might show something that is complementary. So it's not, it's really, since indeed it's research and we don't exactly know what's happening, there's many frontiers and we need different means of tackling them. A collider is one of them, and it is kind of maybe the most broad, if you want, the yeah, so because it very directly goes to that energy scale of the universe, but there are more indirect methods that for instance, concern flavor or whatever, that are very interesting, very important to do, and that are also somewhat more affordable. So I don't think there is, I mean, at least I don't think there is only one way. And also the European strategy proposes multiple ways of tackling the big questions about the universe.
I think the strategy proposes, first of all, a feasibility studies, isn't it, to see what's out there.
Right,
Yeah, I
but
was
in
just gonna
parallel, there are also experiments ongoing. There's directed dark matter detection experiments in mines that are looking directly for particles that were created at that time. There's axion experiments. For instance, we're building one here at DAISY that is also looking for a dark matter candidate, which has a smaller scale. So yes, so while we're also doing the R&D to develop the next collider, we are also doing other experiments that are complementary to that.
Somebody,
I was going to say that the question about collapsing the wave function is a very old puzzle, I'll say, that hasn't been resolved. But Ursula answered it right. She says, I'm an experimentalist. So I find now today that there's many good ideas coming out of our theoretical physicists, and but they're desperate for some guidance from the experimental world about what is really happening in the world. It doesn't matter what they think, it's what gets confirmed by an experiment. And so we're at a point here where I think a large fraction of our theoretical community is looking for some guidance from the experimentalists. Hence building a new machine.
Hence building a new machine. Okay, let's. I want to sort of try. I've got another question. There are one or two questions from the audience. I'd like to try a little curveball here. Something that we have prepped a little bit, I must admit. A new machine, new experimentation. There's a lot of experimentation, as you all know, in space exploration. What about particle physics in space? I mean, you know, this 100-kilometer ring would stretch. I mean, my geography is terrible, but it looks like it's going to be bigger than Geneva, obviously, and cross borders. Why couldn't you just stick that on the moon?
Well, I'm
Nigel, don't back out now
answer.
Because this was your idea.
Yeah. No, it's not my idea, but I'll say that there is an experiment now, a particle physics experiment on the International Space Station, which has been studying the properties of high energy particles coming from interstellar space. It's studying particles coming from the center of our galaxy to understand more about that black hole in the middle of our galaxy. So we're getting out there, and now I think the real question will be, is there an advantage to being on the moon? I looked this up. I was quite surprised. You know, most of us probably think there's no atmosphere on the moon, but if you look it up, NASA will tell you there is an atmosphere on the moon. So, okay, I didn't know that. I thought it was going to be cold on the moon. I didn't realize it was very hot on the moon. So,
that's
Mars.
Mars is cold.
Yeah, no, the moon actually is very hot. In fact, the astronauts had to deal with very high temperatures. Mm-hmm. So it's hot in the day and cold at night. So then I thought, well, I'll go to the dark side of the moon, but of course that's just naive. That's you know, the fact that I can't see it doesn't mean that it's cold and dark. So you know, we have to give some thought to this, but I think there's potential because if it's easier to do something, certainly there's a vacuum that's much better than there is in the U.S. In the U.S., I'll say in the world. Then there might be advantages to be in an environment that has low vacuum, low gravity, cold temperatures at various times and so on. So, it's not crazy to think about it. I think Fermi was the first one to think about this. He suggested putting it around the Earth. But I'm convinced we will go to the moon in the next couple of decades. And it's a question of whether particle physicists want to be there doing stuff. I think it's a good idea.
I mean, there are specific experiments that work better in space, as you're describing there. Mm-hmm. I can hear a voice there.
There is also very. It makes me just think of something else, which is the LISA experiment. It's
yes, exactly.
For gravitational waves, where you shoot laser lights over millions of kilometers into small satellites that are floating. I don't know yet. Haven't never thought if you could do something like that with particle beams, and shooting them over the universe, but maybe.
So let's would you put your money into that, Jeremy?
Yeah, if the other three say yes, then I'll go with it.
Beata, did you say yes?
Idea is to generate energy, which would be very beneficial for mankind in general, because we need a lot of power. So one needs, but okay.
Oh, that's what I was wondering about. Yes, of course, a solar powered accelerator. That'll be the next big challenge, or certainly for a large collider. Let me just ask you this. I want to sort of broaden this out again as we sort of creep towards the end of the hour. And Beata, you did speak a little bit about this. Why is it that kids lose interest in math and that? So what would you tell a secondary school student to motivate them to jump into research in this field without guaranteed discoveries? I mean, that's a very good point. You're sort of looking for things that may or may not be there. But also, and I think this is the integral point that is not part of this question, but how do you get people to stay in these fields and rather than being lured away into other sort of easier fields where there are quicker wins, for instance? So how do you get kids to get into it and stay in it?
I don't know. I think it's just about curiosity, and I also think it's fine. I think it's good if there's cross-fertilization when some people start in one area and then move to another one. I think it's really curiosity. It's fun to try. I mean, this is the luxury as a scientist, that you can stay curious. You can just try to figure things out, just like a kid does figure things out, being curious. So I don't know. I think that's enough attraction, to be honest. I mean, of course, not everybody needs to be a scientist. So the salaries can never compete with, I don't know, whatever. I mean, somehow banking, but you get rewarded because you get to figure out how the universe works or how a virus works. So, I mean, I'm completely addicted to the podcast of Christian Drosten, for instance, because I just learn all these things about that I have no idea about. So I mean, it's just a question of being curious and trying to learn something or figuring something out.
For those who don't know, Christian Drosten, he's become Germany's spokesperson on COVID at the Berlin Charité Hospital. Got one small question here as we get closer to the end, because you mentioned money there as well. So you're not getting paid the big bucks. How can Cern justify the cost of this new collider? You've each got 10 seconds. What would you suggest would be a good justification? Starting with Ursula, perhaps. 10 seconds.
Well, I would say it justifies the cost because everybody in the world who wants to contribute will contribute, and therefore the cost over the whole planet is not that high.
Okay, Nigel?
I think the cost should not be the primary consideration. I think it's all the benefits that it brings to the next generation of young people.
Jeremy?
Because I think it's arguably the most inspirational project and areas going on in science at the moment. It's part of our culture, and ultimately it will provide solutions to some of the greatest challenges of the 21st century.
And Beata?
I think it's a price worth paying, because you learn a lot of interesting science and you get spin-offs. At the end of the day, the cost is of about like €2 per year per EU citizen. That's worth it.
It's a bargain. It's a bargain. Who wouldn't buy it?
One coffee a year per EU.
Yeah, one coffee a year. Oh, well, it's cheap coffee where you're living, right? Listen,
Well,
we've come to the end of our hour. I want to thank all of you, Ursula Basser, Jeremy Farrer, Beate Heinemann, and Nigel Lockyer, and also our puppet master, Rolf Dieter Heyer. This has been great. Don't miss the daily highlights. I have to say, every day at noon GMT, 1 p.m. Berlin time or CET. Find out what's coming up, what's been, so you can catch up on stuff at Falling Walls. The next Falling Walls Circle Table, 6 p.m. Berlin time CET, is how has COVID-19 affected how we pursue science? Jeremy, that's one for you. You can access all the sessions at fallingwalls.com. That's fallingwalls-.com. Check out the website for the entire program. There's like 200 individual events. This has been fantastic. I'm Zulfikar Rabbani. You've been great for your audience participation. Thank you so much for all your questions. And to our guests, Ursula, Jeremy, Beate, Nigel, thank you very much. Thank you and goodbye.